Now next we have to study the general equation of your progressive waves. Now the progressive waves, obviously the waves which will continuously travel in a given direction, has, you can say that, the fixed amplitude and frequency which will generate. So those are nothing but the progressive waves. So you can say that, so it having the constant amplitude. So as the wave in motion, the displacement is a function of space as well as time, and it is given by this, the given equation. Either you can write it down, this one also, that is a sine of omega t. So that is how we used to write it down. Again then omega t minus kx. Yeah, so then when we just talk about that sine of omega t minus kx, so that it is nothing but, obviously now the wave is getting displaced. Yeah, so the wave is moving towards the right side. When I'm saying that it is omega t minus kx, yeah, so for that particular case, so we will say that the wave is moving towards the right side, and if it is, if I'm writing it down as a sine of omega t plus kx, the wave is moving towards the left side. Yeah, and that phi, again we can say that it is nothing but the phase shift for this particular case over here. So now when I'm talking about this omega t minus kx, so let's say this, consider the particle p which is at a distance x. Yeah, so now we know that, so the lambda corresponds to a phase shift of 2 pi, then this distance x corresponds to a phase shift of how much? So definitely we can say that this is a 2 pi x upon lambda. So the phase shift correspond to this point p is nothing but 2 pi x upon lambda. Yeah, so that is how we can say about that your phase shift over here. So definitely after a certain interval of time it starts vibrating. Yeah, so the first particle which is at O over here, it starts vibrating, then finally this vibrations reach up to the point P. Yeah, so by that time, so you can say that, so definitely that angular displacement, yeah, so this is nothing but 2 pi x upon lambda, so which you can show over here, and that is nothing but 2 pi x upon lambda, which I have shown over here. So similarly, what is that phase difference? The relation between the phase difference and path difference. So the phase difference is given as nothing but 2 pi by lambda into path difference. So this is how we can say the relation between this phase difference. Generally we are saying that it is a PD, and obviously the path difference, that is a distance traveled. So the phase correspond to that distance travel, you can write it down. So that is k is equals to, we are also going to call that as a k or beta. So this k is equals to 2 pi by lambda over here. So for this given wave, so if you observe it very carefully, the blue one is nothing but y is equals to a sine omega t. Now the next one, if you see that, so this is y is equals to a sine omega t, that is again, that is a minus pi by 2. Now the wave has get shifted, so the wave has get shifted towards the right side. Yeah, it has got shifted towards the right side by minus, that is obviously by pi by 2. So this is how the phase difference between them is nothing but pi by 2, where you can show the two waves over here for this particular case. Now, so if you want to calculate the energy associated with unit volume of a wave, what is the energy density? Yeah, so the energy density is given by a simple formula, that is a half rho v square. Again you can say that, so this v square, again you can just put in terms of that your amplitude k, omega and phi, which are constant. Yeah, so which are nothing but obviously angular wave number, that frequency and initial phase of the wave. So this is how we can calculate the energy associated or the intensity of your or power transmitted by a string wave. So you can also calculate the power transmitted. Yeah, so intensity is nothing but power upon, that is a 4 pi x square. So with the help of this formula, you can also prove the power transmitted is half mu omega square a square into v over here for this particular case.